Hi everyone, I'm finally making this video about Kepler's law and the lab associated with it. Hopefully it won't be that long. It's a fairly straightforward video once you know what you're doing, but I'm going to go over some of the major highlights and point out some of the issues that you might have, but you should have this worksheet. It's about 3, 4 pages long, something like that. Um, and then you also need to have, let me see, the Mercury orbit printout. So this is a printout of Mercury's orbit, and a little bit about this is we made this at Stephen F. Austin when I was there. This is a very accurate representation of Mercury and its orbit in a slight ellipse. So you can see over here that each one of these little plus signs, these crosses, are actually what Mercury's orbit is. And you can see as it gets up here, this dotted line is a true circle. So you can see Mercury's orbit is not a true circle. In fact, none of the planet's orbits or anything really is 100% a true circle. It's slightly eccentric. Um, but let's go over the first law. So you're going to need to print that out in some form or fashion somehow. You I don't see any way that you could do this on a computer. I mean, I guess you could and measure with a ruler on your monitor or something, but I mean, if you can, feel free. But I would highly recommend that you actually print this out. So, Law 1, a little bit about Law 1. Law 1 states that all things orbit in ellipses. And what we're actually doing is proving that. So the instructions are fairly straightforward. I mean, uh, read it, and you know, just follow along. I think me and another of my colleagues wrote this. I think it's fairly on the nose, just to be frank. But um, just to give you an idea what you need to do, just off the cuff, is first off, you need to get the other focus points. So an ellipse has two focus points, unless it's a circle. A circle is a very special kind of ellipse, but since this is a not a circle, it's an ellipse. You need to get the other focus point. So what you do here is you measure the major axis, which is this line running through the center here, and then you need to half it. So let's say it's not, but just let's say it was like, I don't know, 10 centimeters. So you would half it, so that would be 5 centimeters, right in the right there. And the other focus point is an equal amount of distance away from this focus point, which is the sun. So let's say it's 5 centimeters, and let's say the sun is 1 centimeter away from the center. So then you would have to go over another centimeter from the center on the opposite side and put your other focus point. Because what we're going to do is you have focus point 2 over here now. You're going to need to pick three particular points in Mercury's orbit of these crosses. It doesn't really matter where, um, but you need to pick three of them. Like maybe two up top, one on the bottom. It really doesn't matter where, because what you're doing is proving this is an ellipse, and it could, if it's an ellipse, which it is, it shouldn't matter like where you pick your points. So you're going to draw a line from the sun to the point you picked, and then you're going to draw a line from the point you picked to focus point number 2, which you should have found and labeled, and it'll be over here somewhere. So you're going to add those numbers up. You're going to measure them in centimeters and add them up. And let's go back here. And you're going to put them there and there to focus point 1, focus point 1 to the point, then the point to focus point 2. And then the total distance, it's going to be, whatever number it happens to be. And then you're going to measure the length of the major axis. That's going to be a number. And then what can you conclude from those measurements? So it's fairly straightforward. And then you're going to have to find the eccentricity, which is how flat the ellipse is. Um, and then tell me if it's a low, moderate, or high eccentricity. And I've given you, what is a lower, moderate, or high eccentricity here. Okay. Law 2 is the law that everybody has trouble with because of the way that the triangles are measured. So, Law 2 is explaining that the the orbit of an object sweeps out equal areas in equal amounts of time. So, let's go back here. So, what this is saying is that every one of these points is an equal amount of time. I forget exactly what amount of time. It doesn't really matter. Let's call it like 1 day. Every day, this is where Mercury has moved. So you can see as we are closer to the sun, over here, this is perihelion, it moves quicker. Because as we get further away from the sun, at the farthest point, way over here, you can see the distance between these two crosses is not as great as the distance between them over here. So it's gravity exerting less of a force on the planet, causing it to move a little bit slower. So this is aphelion. So if we were to take an equal amount of days, I believe we have you doing 5 days. Count 5 intervals of time from point A in a counterclockwise motion. So it says circle a point on the orbit about the major axis, but close to perihelion. So perihelion is the point closest to the sun. So let's say you had this point. So you would circle this point or mark it somehow and then count 5 days. So 1, 2, 3, 4, 5. Right? So you would, from over here, or do we have it here? You would draw a line, then count 1, 2, 3, 4, 5, and then draw another line to the sun. Focus point 2 doesn't matter anymore. Don't worry about focus point 2 at all. If you use focus point 2, it's not going to work. You're going to get really messed up measurements. So, what you're doing is essentially making a triangle. So here to the sun, and then 1, 2, 3, 4, 5, this point to the sun, and then you will connect these 2 points, and you're going to have a triangle. Now, a triangle is 1/2 base times height. So your base of your triangle is going to be the largest side of the triangle, the longest side of the triangle. And it's always going to be the side that is closest to aphelion. So whatever side of your triangle that you have is going to be closest to aphelion. So it's going to be this side. It's not going to be the side that's closest to perihelion. Okay. And whenever you're making your triangle, you need your height. Okay, the height is actually, so let's say that, I really wish I could draw on this, but I don't think I can. I haven't really messed around with it. Yeah, I don't think I can draw on this, so I'm just going to have to explain it as best as I possibly can. Your triangle here is not a right triangle. So the side that you draw, like from, where did we have it? 1, 2, 3, 4, 5. Like here to here, that line that you draw here, that is not the height of your line. Okay, the height of your line is from the vertex of your triangle that's opposite from the base. So remember I said your base was the longest side that is closest to aphelion. the vertex, you have to draw a line straight down that hits the base of your triangle, and it makes a right angle with the base. So it needs to be perpendicular to the base. So the vertex here, you're going to draw it straight down, and it's going to hit the base of your triangle and make a right angle. That that is the height of your triangle. So that's the height in the 1/2 base times height. Okay, what people do, and this gets you inaccurate results. People will measure the the height as the part of the triangle where you connected these two parts, and that's going to get you wrong answers. You have to take the vertex that is opposite of your base and draw it straight down and have it perpendicularly, if that's a word, intersect with the base. Um, so that's all I can give you from that. I hope I explained it well enough because I can't really draw on a document file, you know. Um, so all of these areas, I'm just going to tell you now, should be the same if you've done it correctly, or approximately the same. So you're going to have 3 different triangles on this image here. Yeah. And then finally, law 3 is the harmonic law, which says that the square of the period is proportional to the cubes, the cubes of the semi-major axis. The semi-major axis is half of the major axis. So whatever you measure your major axis as, it's going to be half of it. So here, whenever you measure your axis, let's go back to the orbit. You're going to have to use this scale. So I would take like a piece of paper and like measure your semi-major axis, that's half of your major axis. Like put two little, like get a blank sheet of paper, put it up there and make 2 little marks on it, like from the center to the end. And then take that paper with the marks and put it down here and see what how long it is, how big it is. So use the AU or kilometers or whatever it tells you to use. Use that in here. Just follow the instructions. Be sure to use the your units correctly. So you're going to need to measure the semi-major axis in AU. Then you're going to have to do p squared equals ka cubed. K is the proportionality constant. And then you're going to find the period in days. So I believe, just to give you a little hint, it should be somewhere around like 88 days or something like that. So K in this instance, since we're dealing with the solar system, is going to be 1. And it's just there to, when Kepler did this, K was 1 year squared over AU cubed. And he actually didn't know that at the time. Later on, when Newton came around, we had this more generalized form, this 4 pi squared over g times little mass plus big mass times a cubed. And this is what we use to weigh the sun. Now, you've already found your A in AU, and you found your P in years. So what we're going to do is we're going to take this big mass, which is the mass of the sun, and we're going to rearrange the equation, which we've done for you here. And you're going to find the actual weight of the sun. So we got rid of the little m. You may be wondering, like, where did the little m go? So the little m goes away because it's insignificant. Imagine, like, weighing an elephant. So the elephant weighs however much it weighs, like, I don't know, a ton, 2,000. I have no idea, but whatever the elephant weighs, imagine a flea jumping on the elephant, right? So what's the elephant gonna weigh? It's still gonna weigh a ton. The flea is insignificant. So little m plus big M. If your little m is much smaller than your big M, which a planet is much, much smaller than the sun, then we can essentially say, just forget about it, right? So, what we're going to do here, so we found all this stuff. We're going to have to do kind of the same thing, but now we're going to actually have to use um, like seconds and kilometers, right? Because we need our mass in kilograms. So now to use the third law, convert the period from years. So we found the years up here. You're going to convert that into seconds. And then it says multiply the period in years by this many seconds per year. So we've given you that. So you multiply that, put it down here. Then you're going to square that number, right? And then you're going to measure the semi-major axis in kilometers using the scale provided. So let's go down here and see we have kilometers. You're going to do the same thing that you did measuring it in AU, but you're going to do that in kilometers. So each one of these numbers, let's say it's 50, you have to do 50 times 10 to the 6th kilometers. So each one of these, it's obviously not 50 kilometers. It's, the size of going from one city to the next, right? It's 50 times 10 to the 6th kilometers. So don't forget that times 10 to the 6th. So you'll do that. You'll need to put that in meters. So you're going to have to multiply it by 1,000 meters per kilometer. So you have it in kilometers, multiply it by 1,000. You're basically upping the 10 to the 6th 3. So it'll be something times 10 to the 9th. And then you're going to cube it. Okay, so you're going to get a huge number here. And you're going to have a very large number here for the period as well, because that's in seconds. But what we've done for you now is now that you have everything in the proper units, meters and seconds, we've given you this value of 4 pi squared over g. It's this number right here, 5.92 times 10 to the 11th, and you have kilogram second squared over meter cubed. So you're going to go back up here. You have your a cubed and p squared over here. You have that. You have everything in this equation now to get the mass of the sun. So your a cubed is going to be the semi-major axis in meters cubed. And your p squared is going to be your period in seconds squared. Okay? And then this 4 pi squared over g, this whole term right here, we've given you down here, 5.92 times 10 to the 11th. So it's this number times your semi-major axis in meters cubed, divided by your period in seconds squared. So it's this, whatever you get here, and whatever you get here. Now, you can easily check your answer. So I do want to see the work. It's just 3 numbers, 2 multiplied and 1 divided. I mean, you can check out, you can go online and check what is the mass of the sun. In fact, we should have already gone over that, or you should have read it in your book. You can go and find it in your book if you want to. It should, I'll just tell you right now, it should be something like 1.99 or 2.0 times 10 to the 30th kilograms. So you're going to get something, you should get a number like that. Okay. So that's basically the whole lab. Pretty short video, 20 minutes, not too long. I will make this due on Wednesday of next week, since this is Thursday. I want to give you a little time to do it, maybe over the weekend or something like that. I'm not really worried about the turn-in date, just that you actually do the lab. So that's the video, and I hope that maybe clarified a little bit of, or a few things. And all right, I will talk to y'all later.